Okay, here we are looking at Ptolemy again, and I got these things fixed, but we'll see if it works now. Basically, the idea I wanted to show you here is these are the simulations that would be using Ptolemy's model for the solar system. These are observations whose premise is that the Earth is stationary and everything moves around it. Now, if I take a look at some of the inner planets, so we're talking, oh, okay, so I can continue with this. This is the model of what the inner planets look like. Now, the blue dot in the center is the Earth, and so you're sitting on the Earth looking at the motions of the inner planets. The two inner planets are Mercury and Venus. Mercury is the one that's in red, and Venus is the one that's in green. The yellow orb there is obviously the sun. The point, though, that you might not be cognizant of yet is that the planets Mercury and Venus never get very far away from the sun. Basically, you never see Mercury and Venus on the other side of the sun. You never see them straight overhead at midnight. You only see them as morning or evening stars. Okay, so that's one key idea. Now, the second idea is when you look at the outer planets, you have something that's similar. And in that particular case, if this thing will come up, and here it is, we'll just have it running. Now we have an example of, I guess, I would presume that red here is Mars. Hopefully I didn't say the previous one was Mars, but Mercury. And in this case, the green one is probably Jupiter. And then again, the sun is the yellow blob there, and then the Earth is the blue thing. So this is what epicycles look like. We would observe the motion of the planets as they appear against the stars, which are out here by where I'm indicating the cursor. So there's a bunch of stars that are all around here that we would be observing the motion here. And the next thing I want to show you is if I turn on, if I get this right, I'll show the motion of this thing as how these things appear and in the night sky. And watch the loop-de-loops. Okay, the loop-de-loops are basically we would be observing the planets moving backwards relative to the fixed stars. Okay, backwards. And that's what the epicycle here is trying to explain, is why do the planets seem to move backwards with respect to the fixed stars. Okay, so that's the idea there. Okay, now the next thing I want to show you is as a little thing, a little movie that you can pick up on YouTube, and I'll just play it straight away here. And that is, there are some folks that made a Lego toy, or used Lego toys and made this thing called an anti-cathera mechanism. And we'll just play it and let you guys watch it. Now, let me make one announcement here, and that is if anybody can build one of these things for me, I'll give you an automatic A in the class. No questions asked. Because obviously, if you can do that, you know a lot about either mechanics, which is essentially physics, and you'll learn the connection between our modeling of the planets and using tools here on Earth for that. It is pretty impressive. Pretty impressive indeed. All right, so that's Ptolemy. And if we continue on with our discussion, we'll notice that, this is the model that he would have. And if you go and look up NAAP, you'll find a simulation of all these things, just as I've shown you here. Again, the basic view that the Greeks had was this. And the next step I would have my face-to-face folks do is try to figure out what are the basic faults with this view. Okay? All right, now the Dark Ages is thought to be dark. Actually, the Dark Ages were not that dark. During this particular time, the Arabs were taking over as far as continuing civilization, if you will. Although there was a schism between a couple of Arabic scientists, and the current Arabian type of civilization is based upon one viewpoint that we don't need to study the nature around us because revelation is all you need. There was a counterpoint to that occurred earlier, which allowed the Arabian type of technology to expand and be just, top-notch, the most impressive thing on the planet for a while, until this other viewpoint was forced upon everybody. As you can see, they translated all the Roman works, and they came through into Europe via Spain. Pretty amazing stuff, and that's why most of the names that we have for stars are Arabic in nature. Medieval church, one can, this is sort of the standard view that people have, that people believed, especially in the Middle Ages, that the earth was flat. It turns out that unless you were a country bumpkin, nobody believed that. That's just a myth, if you will. So that's something that folks can look into a little bit more. But anyway, the idea that heaven is above us and hell is below us is a pretty strong one. And Dante's Inferno is a good example of one of these similes out there. Here is some late medieval scientists basically putting the kibosh on a lot of ideas that Aristotle had. And even the Greeks at Aristotle's time had problems with Aristotle, especially how things moved. So the next step that we typically go to is in the Renaissance. And basically the idea there is, up until this point, there wasn't really any a lot of expansion on the Greek knowledge. Now, I said that people had problems with Aristotle, but I mean really expanding upon the knowledge. It really took observation and explanation of observation to get us out of these doldrums, if you will. And one of the major things I want to get across is this idea here, that the Greeks didn't know about, they didn't know everything, and the point being is they didn't know about the whole Americas. There was a whole set of civilizations going on in the Americas that were just as amazing as what was going on in Eurasia and Africa at the time. There was probably more people living in the Americas than on the other continents in the world. And the Greeks didn't know about chocolate. They did not know about oranges. I don't know about you, but my girlfriend can't live without chocolate. And I have a sweet tooth too. But what are the things that the Greeks didn't know about? I mean, they didn't know about all sorts of things, you know, new foods, animals, people, whole continents they didn't know. And so when this information came back from like Columbus, and you know, I just use his name because it's off the top of my head. But if you think about all these new discoveries of Europeans of the Americas, then the question comes about rather naturally is what else didn't the Greeks know about? And then we had a couple of really strange things happen. One is we had a couple of supernovas. Both are type 1a supernovas. And basically you had something that was as bright as a sun appearing in the daytime. Right? You had a star that was so bright you could see it during the daytime. That is not normal. What about this idea that the Greeks had, that the cosmos was unchanging? Here we have a big change. Not only does the star appear, pop out of the middle of nowhere, you can see it during the daytime as well as the night. It's really bright. But then it went away. And then you had this great comet of 1577, and basically Tycho Brahe, which we'll find out in a minute, he actually measured the distance to that object by using parallax ideas or trigonometry. Now, I know everybody is fearful of mathematics, but as I keep on saying, how can you tell score without it? All right, so basically at this point we say that God and science get divorced, okay, and heliocentrism rules the universe. Well, at least for a little while. But you do have some, you know, you have this guy Copernicus, and he wrote this book. We call it the Copernican Revolution, but I don't know, he wasn't that brave. He had some really strange ideas too. He used epicycles, but the only thing that his system worked well was it explained the retrograde motion, which we saw before, the loop-de-loops, if you will, in the epicycles. His idea that the sun was at the center explains this loop-de-loop behavior in a very natural way. Okay, so the idea of the natural way is described here, and basically as one object passes another, then against the fixed stars, and again they are very, very far away, and this is an example of Mars's orbit relative to the Earth, that you see over here that Earth moves from 1 to 2, and then as Mars goes from 1 to 2, you see a movement in the background like this, but then as you close in on it, then you go from 3 and then back to 4 and then to 5, and then you start moving again in the same direction. So this idea of loop-de-loops in epicycles is unnecessary if you have the Earth orbiting inside of Mars. And then you have the same behavior for those guys that are closer to the Sun, Mercury and Venus specifically. You could figure out the relative distances to the inferior planets by using trigonometry. You know that the distance, call it d. You know the distance between the Sun and the Earth. to some relative number. You don't know its number in miles, say, but you can represent it as a variable. And then you can look for the time when Venus is the furthest away from the sun. And when that occurs, then this is a right angle. And trigonometry, a gift from the Egyptians, allows us to determine what this little d is relative to the big D. This angle, naturally, you can measure. You can measure the angular distance between the sun and Venus, or between the sun and any planet. And the same is true for the superior planets. It's a little bit more difficult, but the idea here is that you can do it. Okay, and the same is true with the planetary periods. You can figure out how long it takes for these guys to go around relative to Earth years. Okay, so the comparison between what Copernicus had and modern values is not too different. And you might question, what have we done over these past 500 years, or actually 600 years? And let me point out the fact that we know, actually in inches and feet, how far away these guys are from the sun. Okay, Copernicus, he just had a relative number, this AU, which is an astronomical unit, the average distance between the Earth and the sun. We know how big an astronomical unit is in inches and feet. That's what we know. And we know the accuracy of that distance to the sun to something like 10 feet. Just astounding. The distance between here and the sun is something like 150 million kilometers. Okay, so we're talking about 150 million times the size or the height of the Palos Verdes Peninsula. Okay, and we know that number to 10 feet, to the height of a one-story building. That's just amazing. Okay, the next person we want to talk about is Tycho Brahe. If you're interested, there's all sorts of odd stories about him. And he had a description of the solar system that was sort of a combination of old style and new style. Okay, so he had the sun at the center, and then everything else went around. No, actually he had the Earth at the center, the moon going around the Earth, and then the sun goes around the Earth, and then everything else goes around the sun. So it's sort of a hybrid between the two things. We know Tycho Brahe because he took really, really good measurements. These measurements were so good that the error in them was something about the fingernail thickness at arm's length. Okay, he did measure the distance to the Great Comet, and remember what we said about the cosmos being perfect and unchanging? Well, comets change, and he measured the distance to that comet. It had to be greater than 3 times the distance to the moon. Okay, now we haven't talked about the Greeks yet, and they figured out the distance to the moon to about 10% accuracy. So that's pretty darn far away. And the moon was perfect and unchanging. And here we go, we have a comet that is further out than the moon, and it is changing. Okay, so pretty amazing stuff this guy found out. Now, this led to some issues, though. His measurements were so good, it led to what was called the Martian catastrophe. Basically, the models that we have at our fingertips right now, historically speaking at this moment, and I'm talking to you, was Copernicus and was the Ptolemaic tables. Okay, so those two tables were our knowledge about this universe at the time, and they had predictions about how Mars would behave in the night sky. And if you take a look at the data I have here, this comes from a Physics Today journal that I belong to. Basically, you find that the measurements are all pretty good here, and then all of a sudden, boom, it really takes a nosedive here. And the prediction is different than the observed value by a whole hell of a lot. Okay, and if we look at that spot in time and we compare the Copernican tables and the Ptolemaic tables versus what is observed, and remember, observation is king here, right? You observe something and everybody else observes the same thing. That's the truth, okay? Now, mind you, you can make errors on measurement, but look at how far off you are here. you're almost minus 5 degrees on one side and plus 5 degrees on the other. And if we look back, the errors that we're talking about, he's getting, errors of an arc minute. That is a 60th of a degree. So we're talking about errors that are like 300 times, that the observation is 300 times worse, or the prediction is 300 times worse than what you would expect given your measurement error. I mean, I don't know about you, but that's like measuring somebody's height today and getting a value, and their real height is like 5 feet, and you make them observation, and their height is really 200 miles. I mean, that's the sort of thing we're talking about. It doesn't make any sense. So, what gives? Well, what it turned out happening is Kepler took these measurements and tried to understand them relative to the mathematics of the time. See, mathematics, that ugly word coming up again. But the point here is, again, you need to keep score. And one of the interesting things about science is if you understand the new mathematics, then you can apply it to problems, or if you will, old problems, and make a name for yourself. And that's essentially what happened here. Kepler was knowledgeable about conic sections, and he used those conic sections to fit the data that he got from Brahe. And he tried to fit circles to it, because remember, circles are perfect. That idea was still there, but it didn't work. So he used ellipses, and when he used ellipses, then they fit. Now there is a stellarium that I have that shows you how he went about doing this. It was pretty interesting how he did it. I wish I was this smart. He basically had to figure out where the Earth was relative to Mars, and then he figured out where Mars was relative to the Earth. Now it turns out that you can do this. You take enough data and you have enough handles to make this thing work. Pretty amazing stuff. So we have Kepler's 3 laws. The first one is that the planets move in ellipses. The second one is equal areas and equal times, and that is another way of saying that you have things that you have a conservation law of angular momentum. The example that one can use for that is, imagine an ice skater, and that ice skater is twirling around on their, in the center, it's spinning around, and then they pull their arms in. What happens? Well, they spin faster, and when they spread their arms out, they slow down. That is angular momentum. And the angular momentum is basically an understanding that as you move your arms out, then you need to slow down, the revolutions slow down in order to maintain the angular momentum. Okay, and his final law was that the periods of the planets going around the sun would be dependent upon their distance away from the sun. So if you take a look at here, we're talking about the period squared is proportional to the distance that the planet is from the sun to the cube power. And basically that means as you get further away from the sun, you slow down. Now we have Galileo. He is the first person to use telescopes to look at the night sky. Tycho Brahe was the last person to make naked eye astronomy and make a name for himself. So Galileo is known for being the first guy to turn a spyglass to the sky. And here's a picture of one of them here. We have 5 big achievements of Galileo in regards to astronomy. There is the story of him dropping balls off the Leaning Tower of Pisa. As I said, pointed spyglass to the heavens. He looked at the moon with a telescope and saw that it has dimples. I mean, if you take a look at the moon with the naked eye, it looks like a billiard ball. It might have different colors to it, but it looks like a billiard ball. It's smooth. But when you look at it through a telescope, you have to do this. When you look at the moon through a telescope, it has a whole bunch of bumps and valleys and, things we call craters. But even more amazing is you look at this figure. you have light areas on the dark region, and you have light areas, well, again, light areas in the dark region, and then you have dark regions in the light area. You can't have that with a billiard ball. You also observe sunspots, and here we go. The sun has got spots, and these spots move from day to day. You can take a look at this. You can look at data from NASA every day and see these things happening. Jupiter has moons. Of course, you can't see that with the naked eye. Although, actually, some people have good enough vision so they can see the moons of Jupiter. But basically, if you look at Jupiter with a telescope, you see these 3 or 4 little star bits that seem to follow it around, like, a dog following its master around. They sort of bound away just like a dog does, and then come back and bring the ball for you to throw and stuff like that. And that's what these moons floating around Jupiter do. Hopefully you're getting the idea that we're sort of negating some of these premises that the Greeks had. I mean, the Earth isn't the only thing that has things going around it. The cosmos is not perfect. And the last thing that sort of puts the nail on the coffin is Venus's rotation or revolution about the sun. Venus has some peculiarities that are really pretty neat. If you remember the simulation and let me pause here and we'll go into the simulation a little bit for Venus in just the next outing.